Hello everybody! Welcome to this second video about data structures in C. Today we're going to finish off the linked lists and let's see what comes up after that. If you have any questions, feel free to put them down in the chat. I'll have a look and or rather I'll keep an eye on it, and when something pertinent I'll start answering the questions right as we go on. Now, as you might remember, the last time we ended up with our little C program that creates three elephants, a list, adds them to the list, and then frees up the list, and then we free up the elephants. If you don't remember, have a look at the previous video, which I'll make sure to link at the end or when this goes online. Now, this list of elephants, the problem was that I sort of alluded to at the end of it, is that, well, it is lovely that we create the elephants and then free them at the end. This is not usually how you operate, right? So let's first go back to actually drawing how this looks like. Again, to just refresh your memory a little bit. So if you remember, we had created, got a big black line there. What we had created was the following, right? We had our list structure, which had the head and the tail. I don't know how to spell tail. I wrote fill instead, but I guess that will do the job. And then we had created our three elephants. If you remember, those were Bluey, and I'm skipping over all the details of what is in here, but that should be okay for the explanation here. These all had addresses, if you remember those. There was like 300, 310. So those are the three data elements that we created. If you look here on those lines here, right? So those are these three lines here. Pretty much our data structure. Then we created our list on this line, and then we started adding these elements to our list. So the first element that we added, well, we created our list structure, which is this thing here that had a, if you remember that, it had a pointer to the data and next to the next element, and we had that for each of our three elephants. I just draw them a bit quicker now, so I don't explain all the things in here. The pointer will have the address of the things they're pointing to. And I shall draw the lines here as well, so point there. Then these items themselves, they had addresses, and I think I gave them 380, 480, and 580, so we can fill these in. So the head was points to that one, and then the next one, that is this line. Then this line says 480 here, 580 here, and then as usual, if there are no, I don't fill them in, right? And then at the other side we had the tail, which I called fail, was this x580. So that is the structure we ended up with in the last video. But what we'd like to do now is find out a way how we can destroy this whole list without having to do that in the same function, because it isn't often normal that we free these things here just in the same function. Usually the location where the list is created, where they're added and where they're freed, isn't in the same function. So how would you do this? Well, what you can do is, of course, that if you free the list here in the detour, we also, let me scroll up to show where that was done here. Remember, we had this list detour here where we start at the head and then loop over the element until we hit null, and that, as you remember, also following, right? We started with the head, which pointed to this one. We looked at next, and if there's a pointer, we skip to that element. If there's a next, we skip to that element, and then when there's no more next, then we stop iterating. And of course, this is pretty good, and we've ended up freeing, we ended up freeing the data element itself, but not what it was pointing to. So although we freed up our little container that has the next pointer and the data pointer, we don't actually free up the elephant itself. Now, of course, what we can do here is that before we free the pointer here, what we can do is do our, elephant detour, and then we do pointer. I mean, that's a terrible name, but this is pretty much what it is. So the first pointer here is actually the iterator, so this pointer is the iterator, and then the pointer that we have in here is actually the pointer to the data. So this of course works. I mean, if we change this and then remove the elements here, then we, sorry, where did my screen go? My compilation screen. So if we then compile, maybe I didn't call it pointer. What did I call it? Now don't remember. Let's find out. Where did that go? Okay, I didn't call it pointer, I called it data, so I did think of that properly beforehand. Data. So if we compile this now, then we get no exceptions, and then when we run valgrind, we get no warnings or errors. So this works. Of course, the whole idea about having this data structure is that it can cope with every different object that we can think of, right? And if we hardcode the detour for a specific element, then this list is no longer an abstract data structure, it's just an elephant list, which is something we want to avoid. Now, how would you go about it? Well, what we can do is, of course, is not only, what we can do is remember when we create the list what sort of element this is, and then depending on that, call a different destructor, or the destructor that frees up the data element here. And that is exactly how most of these things work. So although we have our list here with our head and the tail, what we can also record is the pointer, or rather a function that knows how to remove a data element of each of the elements that are stored on the list. And a common way to do it is with a detour pointer function. A pointer function is a pointer to a function, which is a new concept that we haven't seen yet. Now, a common way to do that is that you define this type, which you use type before. The destructor is not going to return anything, so hence it's void. But it is a function pointer, and that's how you use the pointer. So this pointer isn't something that exists right now, but it's basically the data type that we are going to name here, which is list detour. So this whole line here, the void pointer list detour, is the data type, and that because it is a function pointer, we haven't defined as a function yet, but we'll do that next. Well, and then it is common that because you never know what sort of data type comes in there, you tend to define these structures with a void type. So pretty much it says we don't know what we're going to store or what we're going to free, but we know for sure it is going to be a function that accepts one pointer. And that's exactly what we do here. So we have this defined now, and then we can now use this list destructor, and we call that, if I type it correctly, I'll align that to make it a bit easier to read. We call that detour. So now we can store this in the list, but of course we also need to store this in when we create the list itself, right? So that's what we end up doing here. So instead of accepting void now, what we actually want to accept is list detour. That is not the right name, because of course we already have list detour, because that's the function we use for the whole list. We want an element detour. And you know, although we have a seater for creating the list element, we don't really have a one for a detour. Well, it'd be nicer actually if we name that correctly, right? So instead of doing the free here, what we're really doing here is of course freeing the list element. So let's do that first, and then we change this to do something else, and hence we have to rename this again, but there we go. So nice way of doing this is that we have list elements, sorry, detour, that doesn't return anything, not a struct, what I'm talking about. You know, it is a function, a void function, detour, that accepts as an element a struct list element, hard to type, which we call e. Oh, this is not PHP code, which we call e. Where's my star? There we go. And then of course this is easy, we call this a free. But now of course we already have this element. What we really want to do is the element data callback, right? And so let's name it that instead. And that means we need to do that here too. And I'll align these to make it a bit easier. I mean, whether you like that in your coding standards or not, that's up to you. So now when we create our lists, we pass in this LList element data detour. And we need to make sure that we of course store that on our list, which is a detour, and then we set the detour that comes in. And because this is a function point, we don't have to add the pointer thing here again. And there we go. And now instead of calling elephant detour when we free up each element in the list, we can now call our data freeing structure. So we know that this list has this detour now, this destructor, that we can then call on the data. Making sure that we remove all the elements there in the bottom, so because we don't want to end up freeing them twice, of course, right? Now, when we now have all these things done, we compile again, and let's hope I didn't make any typos. I did make any typos. Well, it makes sense, right? Because it's telling me that there are too few arguments to the function LLSCTOR, because we've now extended this by also requiring a function pointer that you can use, or that the list can use to free up the data element when the list gets freed itself. So we need to specify that function. Now, we call that, in this case, is an elephant detour. So that's the name of a function that we already defined a bit earlier. So that's the one we have here, right? Now, the thing is, if you compile this, you get an error message. And the error message is, it says it's an incompatible pointer type. It says when we create the elephant list with calling the list CTOR, we're calling elephant detour, but what it expects is a void pointer to struct elephant pointer. But what we have it given, it says list element data detour is what it wanted was a void pointer and then a void pointer, and not a void and then a struct elephant pointer. So we need to change this function a little bit to accept a void pointer here. A void pointer, let's call it data. Now, if we do this, let me comment this out a little bit to show what it does. Let me call this E. If we compile this now, so let me free this up a little bit. It doesn't complain about the function itself anymore, but it now complains about a concept called dereferencing a void pointer. Because the C compiler doesn't understand the data that is part of this void pointer. A void pointer is basically saying it's a pointer to something. It doesn't tell you what it is pointing to. It now no longer understands that E name and E color are elements of the elephant. So yeah, this doesn't work well either then, right? There are two ways to do this nicely. We can either leave our elephant detour as we had and then create a wrapper function, which I think is what my favorite is. So we say elephant, not elephant list detour which accepts our void pointer, which is called this data because it's random data, it's not a list. An unspecified list element, and then what we can do is we can call our original elephant detour and then cast our pointer to a struct elephant pointer. So we can do, so this is how we do cast in C and then specify that with a D. And now the only thing we need to make sure that we update our list call, because we have no longer instantly calling the elephant detour, but we now need to call elephant list detour. And that is of course what's done here. When we recreate a list, we need to specify our new wrapper function. So here we have our new wrapper function. And now this compiles again without any errors, which is what we want. And now we can run valgrind and we get the expected result, right? I mean, we get 13 Alex, 13 trees, and no bits of memory are still available. So yeah, this is a way of cleaning up our list and automatically also freeing up the data elements, which is exactly what we want to do here. So that's lovely. Now, it is always fun that if you have a list that we have here now with all the 3 elements. So let me run GDB and set our GDB, I don't want to compile, set a breakpoint on the line just before we do our list detour. So since the last video, I actually did manage to change the style so that the addresses are now readable. So it says now in yellow instead of blue, the 142F. So we run this, and now let's have a look what's in the elephants. And it now says, well, we have the head, the tail, which is what points to our data, and we have our detour now, which is, well, GDB already knows that this is the elephant list detour, which is the function that we've defined. So this is all good. But let's have a look what is in the list, right? We have this, let me clear this, put this at the top. So we have this list element. When we want to see the data, we get this void pointer because, again, the list structure is supposed to be abstract, so we have to cast that. If I know how to type pointer, and then of course we need to imagine what's in there. So you get bluey and color, which is what we had before. We do that for the, I can't type today. We do that for sunny, and then we have one more if you remember, woolly, and then if we try this once more, we will get an error because next is empty. So if we print that, of course, we need to look at this whole element. Sorry, I keep forgetting the point here. You see what's in here, right? So you have the data element, but next is empty. It's a null pointer. So that's lovely. But looping over this in a debug is, of course, not often what you want to do. What you really want to do is you want to programmatically loop over this list. And, well, how would you do that? Well, you do that in a sort of similar way. What we want to have is a function that, independent of what data we actually have stored in the list, can walk over the list and do something on each of these data elements. And yeah, let's figure out how to add that. Now, we call this function a walker often. So we call this list walk, and we want to walk over the elephants list. But of course, we need to tell it what to do. And just like having a callback for the detour, we can also have a function pointer to operate on a specific element. In this case, what we want to do is show elephant info, right? That's what we want to do for every elephant. And now, of course, we need to define this function and then also add the list walk function to be able to do this. So let's first do the show elephant info function. I probably should start splitting this up in multiple things. So we already have this elephant dump function from the previous one, but because this is something that is going to be applied on an abstract list, we can't use the real data type that we want to dump, which is struct elephant. So in that case, we do again we need to do this void pointer. And then what we can do in here is we can call our original dumping function, elephant dump, and then we do this cast again to struct elephant pointer, and then that's the void pointer that we put in, which is D, which I had forgotten to name here. So that's simple enough. As I said, we need to create this llist walk function as well. So we have done our detour here, but what we now need to do is create another one where we do a walk, and pretty much that loops over our original list, or LL list for linked list, and then we have this function call again, right? This basically a callback function, and we call this llist callback, and then we call it CB, and we'll define those in a moment. Now, looping over a whole list is done in a very similar way as what we have done here, except that we are not going to free the data, because we start at the start. As long as we have a pointer, we show the data, and in this case we can just do pointer next. Ooh, what did I do? We can do pointer next at the end, because we don't need to do any freeing with it. So just doing this will loop over the whole list, right? I mean, we start at the head. We start at the head here. If this pointer, if there's a data element, then we show the data. We call the callback with the data that we have. In this case, callback data. And then we check whether there's a next element. And then the while loop sees, well, if there's an element now, then we do the callback on this data, and so on and so on. So that's simple enough. What we still need to do is, of course, define this llist callback function. So let's do that in the same place as where we define a destructor. So we say llist element callback, and that gets the void pointer. Well, because we don't have to store this, we don't have to modify this on this list element, but we need to remember that llist element callback is now the name of our callback data type. And this data type, again, defines the return of this, which is nothing at the moment, and it has it accepts the data object itself, which is in this case an elephant each, of course. Okay, so I've defined our callback. We didn't, how do we end up calling it? Is llist element callback, not just callback here. We need to remember that. Then we need to remember also that we call that when we walk the lists. And this is, I call this show elephant info here, which is fine. The show elephant function here, where is the elephant function? Elephant show here is the same data type, right? It's a void pointer, a void for returning, so return nothing, and then accepts the data element here. So this should do the job. So if we compile this, let me quit, yes, quit, call GCC, and then I have made an error here. So it says it doesn't know show elephant info. That makes sense because we've called it elephant show, as you can see here. So if we change that, elephant info, then we are there. If we compile this now, this works, and when we run our program, try do in GDB, in case we have an error, go run, and we get the right result, right? We said get bluey is blue, sunny is yellow, and woolly is brown. So this is a way of having a callback here. But what is actually really common to do is that instead of just being able to operate on a data element, sometimes it's important to have context. For example, in case if we don't want to call our original function, but depending on like something, we want to have another void pointer, for example. Now, as an example here is that you see that in this case we do is, right, as a word here. What if sometimes we want to call is and sometimes we want to call an arrow. There's currently no way of doing it because our show elephant info only gets this one element, which is its own data type. There's no context to decide on what to do with that. So what we want now is a context where we can decide whether it is going to be is or a equal sign, for example. Now, because again, we don't want to take assumptions about what context can be, we define it as a void function. We call it context. Sometimes you see also ctext, but let's spell it out for now fully. And instead of doing our elephant dump function, what we want to do is that, well, first of all, we have our elephant, which is the cast that we do here. So that's a struct elephant called E, a pointer is, and then we do our cast struct elephant pointer D. So that is pretty much removing this parameter passing here. We just define a variable to do so that we can do things here. And instead of doing the whole print here, what we're doing here is, well, we'll do a print f. We do s and then another s that can either be the arrow or the word is, the data, and then enter. And then, well, we do ename. This we'll define in a moment, and then eColor to print this information to the screen. Now, this other void pointer, what we need to do is what we need to really pass in here is a character pointer, right? We want to pass in a string. So this is also something that we need to cast first. So we have our character pointer, which is our delimiter, and then we also need to cast the context here to do so. So now we have ename depending on what our character pointer is. So we can do C here, which is what our context is that we're going to pass in. So this is fine. We don't need our elephant dump function anymore, I believe. So I'll remove that. But we need to modify the place where the walker function calls us, as well as the data type itself, to make sure that we can actually pass in this context. So if we go back to the definition here, so the element callback is now getting another data type, which is our context. And now if we compile this, we will get an error, because our callback says it's too few arguments to the function callback on the line 109, because what we want to pass in is our context. But in this place, we also don't have our context defined yet, because we need to feed that to the list walk function. So we're just going to add that to the list walk function, context, and then when we call list walk, we need to specify that. And for example, we say is really, for example. Now when we compile this, we get no errors, and then when we run this, it says blue is really blue and sunny is really yellow. But if I change this for something else, for example, we type the arrow character here, then if we compile this and run this, now you get the arrow without having to make any changes to our data types, and still be able to do multiple things on this walker. Now, of course, doing it with a simple arrow is kind of pointless, but what it is often used for is adding things to a longer data structure. So instead of just passing something static here, what is quite a common thing to do is, like, we want to create a list with all the elephants in there and then store that in a variable, for example. And, well, we can do that as well, of course. But I think I'll leave that for another video in the future. Now, what we've looked at so far is we've cleaned up the list, we finished that, and walking through the list. Now let's go back to figuring out how the operations look like for deleting elements in our list. So let's go back to the drawing that I made and have a look at what's on there. Now if we look at this, at our diagram here, what do we need to do to remove the first element? What changes do we need to make to remove the first element? Now, if you look at it, what needs to happen is that the head pointer needs to point to the next element. Now, how would we go about doing that and also still freeing up the data? So let's say the operation that we want to do is remove the head element. Okay, so we go to the head, we follow that, we know what the head is, it points to this data structure. The first thing that we need to do is we need to free our data element, bluey here, which we can do through our callback that we have just defined now. Then we need to free up this data structure, and we need to set the head to the next element. And that's it. Now, doing that in programming isn't very hard to do, so let's just go switch to that and implement this. So we add our 3 elephants, and then we'll remove the heads. That's basically what we want to do, but this tends to have a different name, and this tends to be an operation called pop. So it doesn't particularly matter what you call these things. In this case, let's just remove the head from our list. And that's all that we really want to do, right? We just want to remove the first element of the list. Now, how do we go about that? Well, I explained that in pseudo code by pointing at my pointers on the paper. But let's just have a look at the implementation. Remove head. Then we have our list. Struct. list, which is our list. And we want to remove the first element. And when I do it on paper, the first thing you want to do is free up the data structure itself, the first data element. But we first need to make sure whether there's actually a head. So if there is, so what you can do is if there is a head, then we do our code. So and then we can say, well, we free up our data element. So we do lists element detour. Sorry, I do this wrong. We do the detour of our data element, which is our head data. Then we can free up our list element itself. So list element detour l head. Then we set, oh, hang on, we can't quite do that because, of course, the moment you free this, we don't know what the next element is again. So we do need to store what the next element is. So the head, the next element, we need to store that before we free it, right? So we have our heads, and then we need to figure out the nexus, and if that is null, that is fine. But we do need to preserve this data, because otherwise, if we would free our list element here, then this pointer is now well, unknown, because we have just freed the containing element. So we need to store this somewhere. But then in the end, we can set the head to next and be done with it. So that's pretty much that we need to do. Let's see what happens if we compile that. Compiles without problems. Shall we run it and see what happens? And indeed, it's freed up here immediately. Let's see whether Valgrind works as well, where we can see any errors. No, it says 14 Alex, 14 freeze, and that's just fine. So removing the head is a simple function, right? It requires a single operation. However, I don't like the code, because everything is now indented, and that is not a nice thing to do. So what I prefer doing, if it is not a head, if there is no head, then we simply return. And then this does not need to be indented. Now, let's see if we compile this. Compiles, and then we can run this, and that works as well. Now, technically, I need to point out that in some older standards of C, it is not okay to create a variable declaration, the void pointer next, after you've already had code. So if your compiler complains about this, or if you need to have it supported by multiple platforms perhaps, then you might have to do something like this, which isn't as nice, but that's how some older C standards work. And most of the code in PHP, for example, is still done with this old standard. We don't have to deal with it here, so I'll do it this way. So it's a very common thing to have all your checks whether your data is valid first up, so that you can return from the function before doing anything else, which is what we've done here. So removing the head is a simple function. Now let's have a look at how we removed the last element in the list. So I'll go back to my drawing and see what we need to do there. Okay, now we are back in our diagram here, right? Now what do we need to do to remove the last element? Well, a shortcut, as you could see, is that we could follow, just like we just follow the head pointer to this first element, we could follow the tail pointer, or fail as I mentioned in this drawing, and do exactly the same thing. So we check where there's a tail, and if there is, we free this the data element that belongs to it, Wooly. We return this data element, and then it becomes tricky, because what do we set the tail pointer to? This data element doesn't have a previous, it only has a next. Now, the two ways you can go about this. You can either, instead of going to the tail pointer directly, you can follow over all the elements until you find the last one, and then update the tail pointer alongside. That is one operation that you can do. Or you can change this linked list that we currently have. It's a single linked list because it points only to the next one. You can modify this data structure to also point to the previous one. So instead of having a pointer next, we also have a previous one. And if you do that, that is called a double linked list. At the moment, I'm not doing that yet. I think in a future video, perhaps not the next one, I will actually look at re-implementing all the single linked list implementations for a double linked list implementation. But in this case, what I want to do first is actually use this data structure that we have to do the same operation. Now, and this is, as you can see, is going to be a bit more complicated because we need to do quite a bit more work, right? Okay, so let's go back to the code. And instead of remove head, we're also going to create a remove tail. Scroll up a little bit so that my face isn't on the way in the video. Remove tail. Now, if there's a tail, there's also always a head, and if there's no head, there's no tail. So we can leave this guard in place if we want to do that. But we need to change the rest to a looping structure. So I'm going to be cheeky and copy that from what we've done with the walking here. Copy this bit here, because I like copy and paste. Paste is in here, and then we can do our operation. Okay, so what we need to do is we need to find the element where next does not exist. That's pretty much what this already does, right? This loops now. Let me make this a bit easier to read. So we start our loop with the head, and we skip to each next item here. Now, the first time we do this, we know that our first element is Bluey, right? We already know that. But when does this loop actually start? Well, it stops the moment next is empty, and we know then at that moment, pointer is already pointing to nil. So what we sort of need to remember, we need to remember the previous item, and this is a bit trickier. Now, a clever way could be is like we can iterate over this until the next element is the tail, because the tail points to the last one. So we can instead do our loop here. we can do, for example, this. We do this until the next element of the thing that we're looping over is the tail. So would this work? Probably would. Let's have a look at the diagram itself. If you remember, if we would only have, what happens if there's no elements in the list? If you just go through this in your head. If there's no elements in the list, head will be null. And as you can see in line 145, that means that we are simply skipping out of the function. So that's a situation where an empty list works. What if there's one element in the list? Now, if there's one element in the list, then what happens here? We do pointer equals pointer next, but that's already going to be nil, right? Because there is no next element. So if we then compare next to ll tail, that wouldn't work, and we continue looping actually end up having a problem. So this doesn't work. So what's in the case if we loop over it until the next, as long as the next element isn't the tail? Does that work? And we'll do all the few situations again. So of course it still works with an empty list. Sorry, I had forgotten this. Does this work? So the first element that we have is pointer next. If there's only one element, pointer next still points to nil. So that's not great either. So that doesn't work. What happens if we do this? So as long as pointer isn't the tail, we do this loop again. And that works for 0 case because we've skipped out of the function. It also works for the case where there's one element. Because if there's one element, the pointer, the head, in this case that we set up in 149, is also the same as the tail. And then we have find our data element. So in this case, we know that at this moment, the element to remove is pointer. Sorry, that's pseudo language. So we shouldn't write code there. So that works. What if there are 3 elements like that we have in our example? Okay, let's play through this. First thing that happens is that the pointer is not the tail. That makes sense, right? Because the head isn't the tail in the first write. So if we skip to the next element is Sunny. And if you look at what Sunny contains, so the list element for Sunny has the pointer at 310 that points to our data element, and then it has next that points to the next element. So that's fine. But the pointer that we have here, which now is 480 because we skipped to the next element, is still not the tail. So that's handy too. So we do our loop once more. So it says pointer equals pointer next. So it says then pointer is 580. And this moment, the pointer is now the tail. Which is great, but we've already forgotten what pointed here. So we also need to keep our previous element as well. So we need to modify this so that we know what the previous element is. So let's do that. So we say, before we skip to the next one, we say pref equals pointer. And we start out our previous is null, because there is no previous element at the start of our list. Okay, does this work? Now, yeah, this should, oh, sorry, let me switch to the code. So yeah, this should work, right? We remember the previous and we know what the next one is. So in order to actually visualize what happens, I think it's a good thing to actually step through this by the code. So we need to change this from remove head to remove tail. Let's compile this. Start GDB. GDB. not this one, this one. And then let's set the breakpoint on our LList walk. Run our code. Do where, shows you what our current location is. So it tells me that we're currently in LList walk on line 106. So let's have a, let me skip on this side to the right line number so we can have the code and what it shows at the same time. So if we do print of the list, it has the head and the tail as we would expect, and so on. So let's now just do line by line. So it says while the pointer. So what is our pointer at the moment? Well, pointer points to the head of the list because we have set it up like that, right? And just a line above really. So that's great. Now then if you look at the while, like because pointer is a nil, we do the next element. So if we do step. Oh, hang on. This is LList walk, not remove head. Remove tail. That's the one we wanted. My apologies. So let me continue running. We stop an LList remove tail now, but the same thing is true, right? We go to LList remove tail. I was demoing the wrong function here, but it's the same idea here. What we do. Well, we first check whether the head is empty. So if we do, we know the head isn't empty, so we can go to the next step. We set our head and our previous. So if we now do pointer, we know it points to data and our next element, and previous doesn't point to anything as we would expect. Next line, it says previous is our current pointer, and then the pointer is next. So if we now do pointer is our second element, the tail is still not the same as the one that follows, and previous is the first element because that should point to our tail. Sorry, our head. Oh, head. And those addresses match, so that's still good. Still what we expect to do. So let's do one more iteration of the loop. We loop over these things. So our previous should now be our second element. So this address is what we have here as a second element. And our pointer points to 420, which is our third element. And if we look into what is in the pointer here, we see that next is now 0. So that's still fine. But at the moment, pointer is still not the same as, it's now the same as tail, so we know that the next element is our tail, and we also still remember the previous element. So that's great. So the loop will now end. And in this moment we have previous points to our second element. So remember, this is the first one, this is the second one, this is the third one. So it points to the second element, because we're removing the third element. And our pointer itself points one further to our last element. And what we want to do is we want to move the previous one to no longer have a next, and we want to have our current one, the one done by pointer, we need to free up. So let's do that. So first of all, we need to call our callback to delete our element. So we call the detour on our data element, which is in pointer, data, and then we need to free that data element itself, which is pointer. And then what we need to do is we need to send the pointer in previous. Next is now going to be null. So this means that we remove, first of all, destroy the data element, then the list element itself, and then set the next one of the previous one to null. Okay, let's compile that again. No errors. When we run this now, we'll get Bluey is blue and Sunny is yellow. And we removed Woolly, which was the last element of our list. As you can remember, we had Bluey, Sunny, and Woolly, but Woolly is now gone from our output. Okay, so let's call this once more. You'd expect that it now should remove Sonny as well, right? So let's compile this, run a test. Oh, now we get an error. That's no good. We did mess up something here. A segmentation fault is always a clear way to show that we have messed up. Let's find out what we messed up here. Now, a clever way is always to use valgrind, because valgrind will tell you the class of error. And we get quite a few here. Okay, let me pipe that through less. What does it say here? Well, it says malloc. It just says it's a lot of things that are being freed. It isn't particularly forthcoming here, right? Just there's lots of stuff. Oh, I know why, because I valgrinded the compiler and not my program. Okay, so this is a better error that we expect. Okay, so what does it say here actually? It says an invalid read of size 8. Size 8 is a pointer. Size 8 is a pointer. And the error happens on line 145. So that is pretty much here. Now we will sort of want to know why this happens, so let's run GDB. Run GDB on a program, we break, this time immediately on the right one, remove tail. So let's do run. And this is our first time we do this, right? So we know that worked, so we skip over this by continuing, and there we go. So now we should be after we have removed Woolly here. So if we do the list, I'm not sure why it says it deleted my breakpoint, but there we go. We see that the head is fine, but the tail looks wrong. You see that? Because remember, 3E0 was the first element, and 420 was our last element, but we've forgotten to update that. Although we changed the pointer in the previous element, what we didn't do is update the tail pointer in the list, which you should have pointed to previous. So that's what our bug was. Because if we do the head, pointer in it, that's still fine. That points to the data and next, which is our 400 one. And if we do next again, that points to 0. That's also fine because that's what we did in the first removal, but we haven't updated our tail pointer. So then when we do the comparison, it would never match, and hence it would break. Oh. So let's compile this again now. GCC. And now run our script, and indeed now we have just Bluey left, which is excellent. Now there's only just that one to leave, so we call the remove tail on that one. Compile again. Run, and again we get a segmentation fault. Why is this now? Well, if we run valgrind, it will tell us why. Oh, I misclicked there. It says now that remove tail, something is wrong on 159. So basically what it says is that there's an invalid write of size 9. And it says address 08 is not stacked, malloc, or recently freed. The 08 indicates it's a very low address, and that is pretty much always related to you doing operations on a null pointer. And that makes sense, right? Because if we remove the last element in our list, we haven't ever updated pref yet, or previous yet. There is no previous element if there's only one element. So we do need to check for that we don't actually end up updating it if it isn't there. So we need to check against that. So only if we have a previous, we need to do this. And also, if there is no previous element, then we know that we need to update our head as well beyond just the tail. So this logically makes more sense. If there is a previous element, then we set the tail to the previous element. We don't need to update the head. And in the case there is no previous element, we can't set pref next because it doesn't exist. And we set where we need to set the tail to null and also set the head to null. So that is logically what you need to do. But as you can see in both cases, if pref is already null, setting tail to null is setting tail to pref at the same time. So you can optimize this by doing it like this. Okay, so let's compile this again. We run it directly with Valgrind, and now again we get no broken output, which is exactly what we want to do. Just to make sure that what happens if we remove one more element from our list, shouldn't do anything that is wrong, and we get no errors because we, of course, when we remove an element from the list, we check whether head is null, which makes perfect sense. All right, now you notice that removing the first element from the list took one operation. Removing the last element from the list took as many operations as we had elements in the lists. And this concept, the complexity of doing an operation, is referred to as the big O notation. The big O notation because it's, as you can expect, it starts with O, or not a 0, it is the O. And the way how you denote these operations, if it's one element, so remove the tail, one element, you write down O1. That's the notation for it. And then if it depends on how many elements there are in the list, which we have for, so I did this the wrong way around, didn't I? It was remove. Okay, let me redraw this bit and I can remove this. Remove head is one operation because we can instantly go to the first one, update our head pointer, and we don't need to deal with the tail pointer. It's a moment at least. And then remove tail meant walking through each element, and more work has to be done. And the notation for having to operate on as many elements as there are in the list is done by n. Now, at some point later, we will come to other operations. For example, we have, if we need to do comparison or sorting between all elements, there is a possibility of having an n squared big O. And n squared means the amount of operations that we need to do our specific thing is the square of the amount of elements that we have. And of course, what you want is you want this operation, if possible, to have it as low as possible, preferably 1 if you can get away with it, or at least something that is linear, which means the algorithm is always going to take a linear amount of elements, still depending on the amount of elements in the list. But what you definitely would want to avoid is doing a square or sometimes like a cube operation. And throughout the rest of the videos, we'll actually have a look at all of these things as well. But so far, we have now implemented our lists. We have looked at some of the operations for walking through the list, for removing elements from the list. And I think we did one thing still wrong, because we haven't tested for removing the head 3 times. So I just want to focus on that before we conclude this video. Well, no, it worked fine. What if we do 4 times? Also fine. So apparently our remove head function worked fine to start with, because that makes perfect sense, right? Because if there's one element, we know that next is null. We remove our data itself, our elephant, we remove our last element, and then we set head to next, because next is already null. We set the head to null, and that is exactly the guard that we have, both for removing the tail and removing the heads. So that is all the operations that we're going to look at. And of course, what is possible to also do is remove an element that is halfway through our linked list but we will do that at some other time for a different data structure. So this concludes our lists. What I want to have a look at in the next video, in the next episode, is a better way of storing simple information about data elements. And the data type that we're going to look at for that is a set. And if there is enough time, then we'll also look at some optimizations on how to make sets even faster. And the common thing for that is called a Bloom filter. Having said that, if there's any questions now, I would be very happy to answer any questions that you have. And yes, somebody's asking, am I too late? Yes, I've just gone through the whole video, but no worries, I'll upload that so you can watch it back. But of course, you can't answer questions afterwards. If there's anything, now's the time. I know there's a little bit of delay between me talking and you being able to type, so I'll give it 30 seconds or so. And if not, then I'll end the video here. I'm not just going to see my face. So what the list that we used here was a simple single linked list is what I used here. But I do want to look in the future at a double linked list as well, and many other data structures. I haven't quite figured out all the things I want to talk about and which order yet, but I think at some point I will add a schedule of all the data types that I want to show at the same time. All right, with no further questions, I hope you enjoyed this. If you want to see the video back, keep an eye out on my on Twitter, or I'm at Derek R, which you see in the bottom of most of my slides. This is still one more question. Does ON only apply to a single linked list? Well, technically, no. ON can apply to other elements as well. Like if you have a double linked list, for example, because you can go forwards and backwards in the list, remove till will also be an O1 operation and not an ON. So yeah, different data types offer you different options about the complexity of your operations, but of course there's trade-offs for that, right? If you have a double linked list, the complexity of maintaining your lists, the links between your elements, is going to be complicated, and it uses more storage space, because at the moment we only store a pointer for to our data as well as to our next element. If we also need a pointer to our previous element, then we have to store 3 pointers, which is 50% more data storage than the single linked list, for example. So there's always going to be trade-offs between having a more complex data type and being able to do operations faster or not. And yeah, that is a trade-off that you need to choose. At the moment, I've just picked a simple linked list first, because that is one of the easier data types to use. But yes, I said I'll go back to a double linked list later where we modify this. But first, in the next video, is going to be sets, and if there's time, also we'll have a look at Bloom filters. Having said that, thank you very much, and I'll see you back next week at the same time.